Recycling is a process to change materials into new products to prevent waste of potentially useful materials, reduce the consumption of fresh raw materials, reduce energy usage, reduce air pollution and water pollution by reducing the need for conventional waste disposal, and lower greenhouse gas emissions as compared to plastic production. Recycling is a key component of modern waste reduction and is the third component of the reduce, reuse and recycle waste hierarchy. There are some ISO standards related to recycling such as ISO 15270-2008 for plastics waste and ISO 14001-2004 for environmental management control of recycling practice. Recyclable materials include many kinds of glass, paper, metal, plastic, textiles, and electronics. The composting or other reuse of biodegradable waste such as food or garden waste is also considered recycling. Materials to be recycled are either brought to a collection center or picked up from the curbside, then sorted, cleaned, and reprocessed into new materials bound for manufacturing. In the strictest sense, recycling of a material would produce a fresh supply of the same material. For example, used office paper would be converted into new office paper, or used foamed polystyrene into new polystyrene. However, this is often difficult or too expensive, so recycling of many products or materials involves their reuse in producing different materials instead. Another form of recycling is the salvage of certain materials from complex products either due to their intrinsic value, or due to their hazardous nature. Critics dispute the net economic and environmental benefits of recycling over its costs, and suggest that proponents of recycling often make matters worse and suffer from confirmation bias. Specifically, critics argue that the costs and energy used in collection and transportation detract from the costs and energy saved in the production process. Also that the jobs produced by the recycling industry can be a poor trade for the jobs lost in logging, mining, and other industries associated with virgin production, and that materials such as paper pulp can only be recycled a few times before material degradation prevents further recycling. Proponents of recycling dispute each of these claims, and the validity of arguments from both sides has led to enduring controversy. History, origins. Recycling has been a common practice for most of human history, with recorded advocates as far back as Plato in 400 BC. During periods when resources were scarce, archaeological studies of ancient waste dumps show less household waste implying more waste was being recycled in the absence of new material. In pre-industrial times, there is evidence of scrap bronze and other metals being collected in Europe and melted down for perpetual reuse. In Britain, dust and ash from wood and coal fires was collected by dustmen and downsiled as a base material used in brick making. The main driver for these types of recycling was the economic advantage of obtaining recycled feedstock instead of acquiring virgin material, as well as a lack of public waste removal in ever more densely populated areas. In 1813, Benjamin Law developed the process of turning rags into shoddy and mungo wool in Batley, Yorkshire. This material combined recycled fibres with virgin wool. The West Yorkshire shoddy industry in towns such as Batley and Dewsbury lasted from the early 19th century to at least 1914. Industrialisation spurred demand for affordable materials. Aside from rags, ferrous scrap metals were coveted as they were cheaper to acquire than was virgin ore. Railroads both purchased and sold scrap metal in the 19th century, and the growing steel and automobile industries purchased scrap in the early 20th century. Many secondary goods were collected, processed, and sold by peddlers who combed dumps, city streets, and went door to door looking for discarded machinery, pots, pans, and other sources of metal. By World War I, thousands of such peddlers roamed the streets of American cities, taking advantage of market forces to recycle post-consumer materials back into industrial production. Beverage bottles were recycled with a refundable deposit at some drink manufacturers in Great Britain and Ireland around 1800, notably Schweppes. An official recycling system with refundable deposits was established in Sweden for bottles in 1884 and aluminium beverage cans in 1982, by law. leading to a recycling rate for beverage containers of €84.99 depending on type, and average use of a glass bottle is over 20 refills. Wartime recycling was a highlight throughout World War II. During the war, financial constraints and significant material shortages due to war efforts made it necessary for countries to reuse goods and recycle materials. It was these resource shortages caused by the world wars, and other such world-changing occurrences that greatly encouraged recycling. The struggles of war claimed much of the material resources available, leaving little for the civilian population. It became necessary for most homes to recycle their waste, as recycling offered an extra source of materials allowing people to make the most of what was available to them. Recycling materials that were used in the household meant more resources were available to support war efforts. This in turn meant a better chance of victory at war. Massive government promotion campaigns were carried out in World War II in every country involved in the war, urging citizens to donate metals and conserve fiber, as a matter of significant patriotic importance. Post-war, a considerable investment in recycling occurred in the 1970s, due to rising energy costs. Recycling aluminium uses only 5% of the energy required by virgin production. Glass, paper and metals have less dramatic but very significant energy savings when recycled feedstock is used. As of 2014, the European Union has about 50% of world share of the waste and recycling industries, with over 60,000 companies employing 500,000 persons, with a turnover of $24 billion. Countries have to reach recycling rates of at least 50%, while the lead countries are around 65% and the EU average is 39% as of 2013. Legislation, supply. For a recycling program to work, having a large, stable supply of recyclable material is crucial. 3 legislative options have been used to create such a supply: mandatory recycling collection, container deposit legislation, and refuse bans. Mandatory collection laws set recycling targets for cities to aim for, usually in the form that a certain percentage of a material must be diverted from the city's waste stream by a target date. The city is then responsible for working to meet this target. Container deposit legislation involves offering a refund for the return of certain containers, typically glass, plastic, and metal. When a product in such a container is purchased, a small surcharge is added to the price. This surcharge can be reclaimed by the consumer if the container is returned to a collection point. These programs have been very successful, often resulting in an 80% recycling rate. Despite such good results, the shift in collection costs from local government to industry and consumers has created strong opposition to the creation of such programs in some areas. A third method of increased supply of recyclates is to ban the disposal of certain materials as waste, often including used oil, old batteries, tires and garden waste. One aim of this method is to create a viable economy for proper disposal of banned products. Care must be taken that enough of these recycling services exist, or such bans simply led to increased illegal dumping. Government-mandated demand legislation has also been used to increase and maintain a demand for recycled materials. 4 methods of such legislation exist: minimum recycled content mandates, utilization rates, procurement policies, recycled product labeling. Both minimum recycled content mandates and utilization rates increase demand directly by forcing manufacturers to include recycling in their operations. Content mandates specify that a certain percentage of a new product must consist of recycled material. Utilization rates are a more flexible option. Industries are permitted to meet the recycling targets at any point of their operation or even contract recycling out in exchange for tradable credits. Opponents to both of these methods point to the large increase in reporting requirements they impose, and claim that they rob industry of necessary flexibility. Governments have used their own purchasing power to increase recycling demand through what are called procurement policies. These policies are either set-asides, which earmark a certain amount of spending solely towards recycled products, or price preference programs which provide a larger budget when recycled items are purchased. Additional regulations can target specific cases. In the United States, for example, the Environmental Protection Agency mandates the purchase of oil, paper, tires and building insulation from recycled or re-refined sources whenever possible. The final government regulation towards increased demand is recycled product labeling. When producers are required to label their packaging with amount of recycled material in the product, consumers are better able to make educated choices. Consumers with sufficient buying power can then choose more environmentally conscious options, prompt producers to increase the amount of recycled material in their products, and indirectly increase demand. Standardized recycling labeling can also have a positive effect on supply of recyclates if the labeling includes information on how and where the product can be recycled. Recyclates. Recyclate is a raw material that is sent to, and processed in a waste recycling plant or materials recovery facility which will be used to form new products. The material is collected in various methods and delivered to a facility where it undergoes remanufacturing so that it can be used in the production of new materials or products. For example, plastic bottles that are collected can be reused and made into plastic pellets, a new product. Quality of recyclate. The quality of recyclates is recognized as one of the principal challenges that needs to be addressed for the success of a long-term vision of a green economy and achieving zero waste. Recyclate quality is generally referring to how much of the raw material is made up of target material compared to the amount of non-target material and other non-recyclable material. Only target material is likely to be recycled, so a higher amount of non-target and non-recyclable material will reduce the quantity of recycling product. A high proportion of non-target and non-recyclable material can make it more difficult for reprocessors to achieve a high quality unregistered trademark recycling. If the recyclate is of poor quality, it is more likely to end up being downcycled or, in more extreme cases, sent to other recovery options or landfill. For example, to facilitate the remanufacturing of clear glass products there are tight restrictions for colored glass going into the remelt process. The quality of recyclate not only supports high-quality recycling, it can deliver significant environmental benefits by reducing, reusing, and keeping products out of landfills. High-quality recycling can help support growth in the economy by maximizing the economic value of the waste material collected. Higher income levels from the sale of quality recyclates can return value which can be significant to local governments, households and businesses. Pursuing high-quality recycling can also provide consumer and business confidence in the waste and resource management sector and may encourage investment in that sector. There are many actions along the recycling supply chain that can influence and affect the material quality of recyclate. It begins with the waste producers who place non-target and non-recyclable wastes in recycling collection. This can affect the quality of final recyclate streams or require further efforts to discard those materials at later stages in the recycling process. The different collection systems can result in different levels of contamination. Depending on which materials are collected together, extra effort is required to sort this material back into separate streams and can significantly reduce the quality of the final product. Transportation and the compaction of materials can make it more difficult to separate material back into separate waste streams. Sorting facilities are not 100% effective in separating materials, despite improvements in technology and quality recyclate which can see a loss in recyclate quality. The storage of materials outside where the product can become wet can cause problems for reprocessors. Reprocessing facilities may require further sorting steps to further reduce the amount of non-target and non-recyclable material. Each action along the recycling path plays a part in the quality of recyclate. Quality Recyclate Action Plan. The Recyclate Quality Action Plan of Scotland sets out a number of proposed actions that the Scottish Government would like to take forward in order to drive up the quality of the materials being collected for recycling and sorted at materials recovery facilities before being exported or sold onto the reprocessing market. The plan unregistered trademark objectives are to drive up the quality of recyclate, deliver greater transparency around the quality of recyclate, provide help to those contracting with materials recycling facilities to identify what is required of them, ensure compliance with the Waste Regulations 2012. Stimulate a household market for quality Recyclate. Address and reduce issues surrounding the waste shipment regulations. The plan focuses on 3 key areas, with 14 actions which were identified to increase the quality of materials collected, sorted and presented to the processing market in Scotland. The 3 areas of focus are, collection systems and input contamination, sorting facilities material sampling and transparency, material quality benchmarking and standards, recycling consumer waste, collection. A number of different systems have been implemented to collect recyclates from the general waste stream. These systems lie along the spectrum of trade-off between public convenience and government ease and expense. The 3 main categories of collection are drop-off centers, buyback centers, and curbside collection. Drop-off centers require the waste producer to carry the recyclates to a central location, either an installed or mobile collection station or the reprocessing plant itself. They are the easiest type of collection to establish, but suffer from low and unpredictable throughput. Buyback centers differ in that the cleaned recyclates are purchased, thus providing a clear incentive for use and creating a stable supply. The post-processed material can then be sold on, hopefully creating a profit. Unfortunately, government subsidies are necessary to make buyback centers a viable enterprise, as according to the United States National Waste and Recycling Association, it costs on average $50 to process a ton of material, which can only be resold for $30. Curbside collection. Curbside collection encompasses many subtly different systems, which differ mostly on where in the process the recyclates are sorted and cleaned. The main categories are mixed waste collection, commingled recyclables and source separation. A waste collection vehicle generally picks up the waste. At one end of the spectrum is mixed waste collection, in which all recyclates are collected mixed in with the rest of the waste, and the desired material is then sorted out and cleaned at a central sorting facility. This results in a large amount of recyclable waste, paper especially, being too soiled to reprocess, but has advantages as well. The city need not pay for a separate collection of recyclates and no public education is needed. Any changes to which materials are recyclable is easy to accommodate as all sorting happens in a central location. In a commingled or single-stream system, all recyclables for collection are mixed but kept separate from other waste. This greatly reduces the need for post-collection cleaning but does require public education on what materials are recyclable. Source separation is the other extreme, where each material is cleaned and sorted prior to collection. This method requires the least post-collection sorting and produces the purest recyclates, but incurs additional operating costs for collection of each separate material. An extensive public education program is also required, which must be successful if recyclate contamination is to be avoided. Source separation used to be the preferred method due to the high sorting costs incurred by commingled collection. Advances in sorting technology, however, have lowered this overhead substantially. Many areas which had developed source separation programs have since switched to commingled collection. Distributed recycling. For some waste materials such as plastic, recent technical devices called RecycleBots enable a form of distributed recycling. Preliminary life cycle analysis, LCA, indicates that such distributed recycling of Hdpe to make filament of 3D printers in rural regions is energetically favorable to either using virgin resin or conventional recycling processes because of reductions in transportation energy, sorting. Once commingled recyclates are collected and delivered to a central collection facility, the different types of materials must be sorted. This is done in a series of stages, many of which involve automated processes such that a truckload of material can be fully sorted in less than an hour. Some plants can now sort the materials automatically, known as single-stream recycling. In plants a variety of materials are sorted such as paper, different types of plastics, glass, metals, food scraps, and most types of batteries. A 30% increase in recycling rates has been seen in the areas where these plants exist. Initially, the commingled recyclates are removed from the collection vehicle and placed on a conveyor belt spread out in a single layer. Large pieces of corrugated fiberboard and plastic bags are removed by hand at this stage, as they can cause later machinery to jam. Next, automated machinery separates the recyclates by weight, splitting lighter paper and plastic from heavier glass and metal. Cardboard is removed from the mixed paper, and the most common types of plastic, PET and HDPE, are collected. This separation is usually done by hand, but has become automated in some sorting centers. A spectroscopic scanner is used to differentiate between different types of paper and plastic based on the absorbed wavelengths, and subsequently divert each material into the proper collection channel. Strong magnets are used to separate out ferrous metals, such as iron, steel, and tin-plated steel cans. Non-ferrous metals are ejected by magnetic eddy currents in which a rotating magnetic field induces an electric current around the aluminum cans, which in turn creates a magnetic eddy current inside the cans. This magnetic eddy current is repulsed by a large magnetic field, and the cans are ejected from the rest of the recyclate stream. Finally, glass must be sorted by hand on the basis of its color, brown, amber, green, or clear. This process of recycling as well as reusing the recycled material proves to be advantageous for many reasons, as it reduces amount of waste sent to landfills, conserves natural resources, saves energy, reduces greenhouse gas emissions, and helps create new jobs. Recycled materials can also be converted into new products that can be consumed again, such as paper, plastic, and glass. The City and County of San Francisco's Department of the Environment offers one of the best recycling programs to support its citywide goal of zero waste by 2020. San Francisco's refuse hauler, Recology, operates an effective recyclable sorting facility in San Francisco, which helped San Francisco reach a record-breaking diversion rate of 80%. Recycling industrial waste. Although many government programs are concentrated on recycling at home, a large portion of waste is generated by industry. The focus of many recycling programs done by industry is the cost-effectiveness of recycling. The ubiquitous nature of cardboard packaging makes cardboard a commonly recycled waste product by companies that deal heavily in packaged goods, like retail stores, warehouses, and distributors of goods. Other industries deal in niche or specialized products, depending on the nature of the waste materials that are present. The glass, lumber, wood pulp, and paper manufacturers all deal directly in commonly recycled materials. However, old rubber tires may be collected and recycled by independent tire dealers for a profit. Levels of metals recycling are generally low. In 2010, the International Resource Panel, hosted by the United Nations Environment Programme, published reports on metal stocks that exist within society and their recycling rates. The panel reported that the increase in the use of metals during the 20th and into the 21st century has led to a substantial shift in metal stocks from below ground to use in applications within society above ground. For example, the in-use stock of copper in the USA grew from 73 to 238 kg per capita between 1932 and 1999. The report authors observed that, as metals are inherently recyclable, the metal stocks in society can serve as huge mines above ground. However, they found that the recycling rates of many metals are very low. The report warned that the recycling rates of some rare metals used in applications such as mobile phones, battery packs for hybrid cars and fuel cells, are so low that unless future end-of-life recycling rates are dramatically stepped up, these critical metals will become unavailable for use in modern technology. The military recycles some metals. The U.S. Navy's ship disposal program uses shipbreaking to reclaim the steel of old vessels. Ships may also be sunk to create an artificial reef. Uranium is a very dense metal that has qualities superior to lead and titanium for many military and industrial uses. The uranium left over from processing it into nuclear weapons and fuel for nuclear reactors is called depleted uranium, and it is used by all branches of the U.S. military use for armor-piercing shells and shielding. The construction industry may recycle concrete and old road surface pavement, selling their waste materials for profit. Some industries, like the renewable energy industry and solar photovoltaic technology in particular, are being proactive in setting up recycling policies even before there is considerable volume to their waste streams, anticipating future demand during their rapid growth. Recycling of plastics is more difficult, as most programs can't reach the necessary level of quality. Recycling of PVC often results in downcycling of the material, which means only products of lower quality standard can be made with the recycled material. A new approach which allows an equal level of quality is the vinyl loop process. It was used after the London Olympics 2012 to fulfill the PVC policy. E-waste recycling. E-waste is a growing problem, accounting for 20 to 50 million metric tons of global waste per year according to the EPA. Many recyclers do not recycle e-waste or do not do so responsibly. The E-Steward certification was created to ensure recyclers are held to the highest standards for environmental responsibility and to give consumers an easy way to identify responsible recyclers. eCycle, LLC, was the first mobile recycling company to be E-Steward certified. Plastic recycling. Plastic recycling is the process of recovering scrap or waste plastic and reprocessing the material into useful products, sometimes completely different in form from their original state. For instance, this could mean melting down soft drink bottles and then casting them as plastic chairs and tables. Physical recycling. Some plastics are remelted to form new plastic objects. For example, PET water bottles can be converted into clothing-grade polyester. A disadvantage of this type of recycling is that in each use and recycling cycle the molecular weight of the polymer can change further and the levels of unwanted substances in the plastic can increase. Chemical recycling. For some polymers it is possible to convert them back into monomers. For example, PET can be treated with an alcohol and a catalyst to form a dialkyl terephthalate. The terephthalate diester can be used with ethylene glycol to form a new polyester polymer. Thus it is possible to make the pure polymer again. Waste plastic pyrolysis to fuel oil. Another process involves the conversion of assorted polymers into petroleum by a much less precise thermal depolymerization process. Such a process would be able to accept almost any polymer or mix of polymers, including thermoset materials such as vulcanized rubber tires and the biopolymers and feathers and other agricultural waste. Like natural petroleum, the chemicals produced can be made into fuels as well as polymers. A RESEM technology plant of this type exists in Carthage, Missouri, USA, using turkey waste as input material. Gasification is a similar process, but is not technically recycling since polymers are not likely to become the result. Plastic pyrolysis can convert petroleum-based waste streams such as plastics into quality fuels, carbons. Given below is the list of suitable plastic raw materials for pyrolysis: mixed plastic, mixed waste plastic from waste paper mill, multi-layered plastic, recycling codes. In order to meet recyclers' needs while providing manufacturers a consistent, uniform system, a coding system is developed. The recycling code for plastics was introduced in 1988 by Plastics Industry through the Society of the Plastics Industry, Incorporated. Because municipal recycling programs traditionally have targeted packaging primarily bottles and containers the resin coding system offered a means of identifying the resin content of bottles and containers commonly found in the residential waste stream. Plastic products are printed with numbers 1 to 7 depending on the type of resin. Type 1 plastic, PET, polyethylene terephthalate, is commonly found in soft drink and water bottles. Type 2, Hdpe, high-density polyethylene is found in most hard plastics such as milk jugs, laundry detergent bottles, and some dishware. Type 3, PVC includes items like shampoo bottles, shower curtains, hula hoops, credit cards, wire jacketing, medical equipment, siding, and piping. Type 4, called LDPE, or low-density polyethylene, is found in shopping bags, squeezable bottles, tote bags, clothing, furniture, and carpet. Type 5 is PP, which stands for polypropylene and makes up syrup bottles, straws, Tupperware, and some automotive parts. Type 6 is PS, polystyrene, and makes up meat trays, egg cartons, clamshell containers and compact disc cases. Type 7 includes all other plastics like bulletproof materials, 3 and 5 gallon water bottles, and sunglasses. Types 1 and 2 are the most commonly recycled. Cost-to-Euro-benefit analysis. There is some debate over whether recycling is economically efficient. It is said that dumping 10,000 tons of waste in a landfill creates 6 jobs, while recycling 10,000 tons of waste can create over 36 jobs. However, the cost-effectiveness of creating the additional jobs remains unproven. According to the U.S. Recycling Economic Informational Study, there are over 50,000 recycling establishments that have created over 1 million jobs in the U.S. 2 years after New York City declared that implementing recycling programs would be a drain on the city, New York City leaders realized that an efficient recycling system could save the city over $20 million. Municipalities often see fiscal benefits from implementing recycling programs, largely due to the reduced landfill costs. A study conducted by the Technical University of Denmark, according to The Economist, found that in 83% of cases, recycling is the most efficient method to dispose of household waste. However, a 2004 assessment by the Danish Environmental Assessment Institute concluded that incineration was the most effective method for disposing of drink containers, even aluminium ones. Fiscal efficiency is separate from economic efficiency. Economic analysis of recycling do not include what economists call externalities, which are unpriced costs and benefits that accrue to individuals outside of private transactions. Examples include decreased air pollution and greenhouse gases from incineration, reduced hazardous waste leaching from landfills, reduced energy consumption, and reduced waste and resource consumption, which leads to a reduction in environmentally damaging mining and timber activity. About 4,000 minerals are known, of these only a few hundred minerals in the world are relatively common. Known reserves of phosphorus will be exhausted within the next 100 years at current rates of usage. Without mechanisms such as taxes or subsidies to internalize externalities, businesses will ignore them despite the costs imposed on society. To make such non-fiscal benefits economically relevant, advocates have pushed for legislative action to increase the demand for recycled materials. The United States Environmental Protection Agency has concluded in favor of recycling, saying that recycling efforts reduced the country's carbon emissions by a net 49 million metric tons in 2005. In the United Kingdom, the Waste and Resources Action Programme stated that Great Britain's recycling efforts reduce CO2 emissions by €15 million tons a year. Recycling is more efficient in densely populated areas, as there are economies of scale involved. Certain requirements must be met for recycling to be economically feasible and environmentally effective. These include an adequate source of recyclates, a system to extract those recyclates from the waste stream, a nearby factory capable of reprocessing the recyclates, and a potential demand for the recycled products. These last two requirements are often overlooked. Without both an industrial market for production using the collected materials and a consumer market for the manufactured goods, recycling is incomplete and in fact only collection. Many economists favor a moderate level of government intervention to provide recycling services. Economists of this mindset probably view product disposal as an externality of production and subsequently argue government is most capable of alleviating such a dilemma. Trade in recyclates. Certain countries trade in unprocessed recyclates. Some have complained that the ultimate fate of recyclates sold to another country is unknown and they may end up in landfills instead of reprocessed. According to one report, in America, 80% of computers destined for recycling are actually not recycled. There are reports of illegal waste imports to China being dismantled and recycled solely for monetary gain, without consideration for workers' health or environmental damage. Although the Chinese government has banned these practices, it has not been able to eradicate them. In 2008, the prices of recyclable waste plummeted before rebounding in 2009. Cardboard averaged about £53 per tonne from 2004 Euro 2008, dropped to £19 per tonne, and then went up to £59 per tonne in May 2009. PET plastic averaged about £156 per tonne, dropped to £75 per tonne and then moved up to £195 per tonne in May 2009. Certain regions have difficulty using or exporting as much of a material as they recycle. This problem is most prevalent with glass. Both Britain and the US import large quantities of wine bottled in green glass. Though much of this glass is sent to be recycled, outside the American Midwest there is not enough wine production to use all of the reprocessed material. The extra must be downsiled into building materials or reinserted into the regular waste stream. Similarly, the northwestern United States has difficulty finding markets for recycled newspaper, given the large number of pulp mills in the region as well as the proximity to Asian markets. In other areas of the U.S., however, demand for used newsprint has seen wide fluctuation. In some U.S. states, a program called Recycle Bank pays people to recycle, receiving money from local municipalities for the reduction in landfill space which must be purchased. It uses a single-stream process in which all material is automatically sorted. Criticisms and responses. Much of the difficulty inherent in recycling comes from the fact that most products are not designed with recycling in mind. The concept of sustainable design aims to solve this problem, and was laid out in the book Cradle to Cradle, Remaking the Way We Make Things by architect William McDonough and chemist Michael Braunart. They suggest that every product should have a complete closed-loop cycle mapped out for each component a way in which every component will either return to the natural ecosystem through biodegradation or be recycled indefinitely. While recycling diverts waste from entering directly into landfill sites, current recycling misses the dissipative components. Complete recycling is impracticable as highly dispersed wastes become so diluted that the energy needed for their recovery becomes increasingly excessive. For example, how will it ever be possible to recycle the numerous chlorinated organic hydrocarbons that have bioaccumulated in animal and human tissues across the globe, the copper dispersed in fungicides, the lead in widely applied paints, or the zinc oxides present in the finely dispersed rubber powder that is abraded from automobile tires? As with environmental economics, care must be taken to ensure a complete view of the costs and benefits involved. For example, paperboard packaging for food products is more easily recycled than most plastic, but is heavier to ship and may result in more waste from spoilage. Energy and material flows. The amount of energy saved through recycling depends upon the material being recycled and the type of energy accounting that is used. Energy analysis. For example, budgets for the amount of energy of one kind that is required to make or transform things into another kind of product or service. Using energy life cycle analysis, researchers have concluded that materials with large refining costs have the greatest potential for high recycle benefits. Moreover, the highest energy efficiency accrues from systems geared toward material recycling, where materials are engineered to recycle back into their original form and purpose, followed by adaptive reuse systems where the materials are recycled into a different kind of product, and then byproduct reuse systems where parts of the products are used to make an entirely different product. The Energy Information Administration states on its website that a paper mill uses 40% less energy to make paper from recycled paper than it does to make paper from fresh lumber. Some critics argue that it takes more energy to produce recycled products than it does to dispose of them in traditional landfill methods, since the curbside collection of recyclables often requires a second waste truck. However, recycling proponents point out that a second timber or logging truck is eliminated when paper is collected for recycling, so the net energy consumption is the same. An energy life cycle analysis on recycling revealed that fly ash, aluminum, recycled concrete aggregate, recycled plastic, and steel yield higher efficiency ratios, whereas the recycling of lumber generates the lowest recycle benefit ratio. Hence, the specific nature of the recycling process, the methods used to analyze the process, and the products involved affect the energy savings budgets. It is difficult to determine the amount of energy consumed or produced in waste disposal processes in broader ecological terms, where causal relations dissipate into complex networks of material and energy flow. For example, cities do not follow all the strategies of ecosystem development. Biogeochemical paths become fairly straight relative to wild ecosystems, with very reduced recycling, resulting in large flows of waste and low total energy efficiencies. By contrast, in wild ecosystems, one population unregistered trademark S wastes are another population unregistered trademark S resources, and succession results in efficient exploitation of available resources. However, even modernized cities may still be in the earliest stages of a succession that may take centuries or millennia to complete. How much energy is used in recycling also depends on the type of material being recycled and the process used to do so. Aluminium is generally agreed to use far less energy when recycled rather than being produced from scratch. The EPA states that recycling aluminum cans, for example, saves 95% of the energy required to make the same amount of aluminum from its virgin source, bauxite. In 2009, more than half of all aluminium cans produced came from recycled aluminium. Economist Stephen Landsberg has suggested that the sole benefit of reducing landfill space is trumped by the energy needed and resulting pollution from the recycling process. Others, however, have calculated through life cycle assessment that producing recycled paper uses less energy and water than harvesting, pulping, processing, and transporting virgin trees. When less recycled paper is used, additional energy is needed to create and maintain farmed forests until these forests are self-sustainable as virgin forests. Other studies have shown that recycling in itself is inefficient to perform the A-O decoupling of economic development from the depletion of non-renewable raw materials that is necessary for sustainable development. The international transportation or recycle material flows through different trade networks of the three countries result in different flows, decay rates, and potential recycling returns. As global consumption of natural resources grows, its depletion is inevitable. The best recycling can do is to delay complete closure of material loops to achieve 100% recycling of known renewables as impossible as microtrace materials dissipate into the environment causing severe damage to the planet's ecosystems. Historically, this was identified as the metabolic rift by Karl Marx, who identified the unequal exchange rate between energy and nutrients flowing from rural areas to feed urban cities that create effluent wastes degrading the planet's ecological capital, such as loss in soil nutrient production. Energy conservation also leads to what is known as Jevons Paradox, where improvements in energy efficiency lowers the cost of production and leads to a rebound effect where rates of consumption and economic growth increases. Costs. The amount of money actually saved through recycling depends on the efficiency of the recycling program used to do it. The Institute for Local Self-Reliance argues that the cost of recycling depends on various factors around a community that recycles, such as landfill fees and the amount of disposal that the community recycles. It states that communities start to save money when they treat recycling as a replacement for their traditional waste system rather than an add-on to it and by redesigning their collection schedules and/or trucks. In some cases, the cost of recyclable materials also exceeds the cost of raw materials. Virgin plastic resin costs 40% less than recycled resin. Additionally, a United States Environmental Protection Agency study that tracked the price of clear glass from July 15 to August 2, 1991, found that the average cost per ton ranged from $40 to $60, while a USGS report shows that the cost per ton of raw silica sand from years 1993 to 1997 fell between $17.33 and $18.10. In a 1996 article for the New York Times, John Tierney argued that it costs more money to recycle the trash of New York City than it does to dispose of it in a landfill. Tierney argued that the recycling process employs people to do the additional waste disposal, sorting, inspecting, and many fees are often charged because the processing costs used to make the end product are often more than the profit from its sale. Tierney also referenced a study conducted by the Solid Waste Association of North America that found in the 6 communities involved in the study, all but one of the curbside recycling programs, and all the composting operations and waste-to-energy incinerators, increased the cost of waste disposal. Tierney also points out that the prices paid for scrap materials are a measure of their environmental value as recyclables. Scrap aluminum fetches a high price because recycling it consumes so much less energy than manufacturing new aluminum. However, comparing the market cost of recyclable material with the cost of new raw materials ignores economic externalities, the costs that are currently not counted by the market. Creating a new piece of plastic, for instance, may cause more pollution and be less sustainable than recycling a similar piece of plastic, but these factors will not be counted in market cost. A life cycle assessment can be used to determine the levels of externalities and decide whether the recycling may be worthwhile despite unfavorable market costs. Alternatively, legal means can be used to bring externalities into the market, so that the market cost of the material becomes close to the true cost. In a 2007 article, Michael Munger, chairman of political science at Duke University, wrote that if recycling is more expensive than using new materials, it can't possibly be efficient. There is a simple test for determining whether something is a resource or just garbage. If someone will pay you for the item, it's a resource, but if you have to pay someone to take the item away, then the item is garbage. In a 2002 article for the Heartland Institute, Jerry Taylor, director of natural resource studies at the Cato Institute, wrote, "If it costs X to deliver newly manufactured plastic to the market, for example, but it costs 10x to deliver reused plastic to the market, we can conclude the resources required to recycle plastic are 10 times more scarce than the resources required to make plastic from scratch." And because recycling is supposed to be about the conservation of resources, mandating recycling under those circumstances will do more harm than good. Working conditions. The recycling of waste electrical and electronic equipment in India and China generates a significant amount of pollution. Informal recycling in an underground economy of these countries has generated an environmental and health disaster. High levels of lead, polybrominated divinyl ethers, polychlorinated dioxins and furans, as well as polybrominated dioxins and furans concentrated in the air, bottom ash, dust, soil, water and sediments in areas surrounding recycling sites. Critics also argue that while recycling may create jobs, they are often jobs with low wages and terrible working conditions. These jobs are sometimes considered to be make-work jobs that don't produce as much as the cost of wages to pay for those jobs. In areas without many environmental regulations and/or worker protections, jobs involved in recycling such as shipbreaking can result in deplorable conditions for both workers and the surrounding communities. Environmental impact. Economist Stephen Landsberg, author of a paper entitled, "Why I Am Not an Environmentalist," has claimed that paper recycling actually reduces tree populations. He argues that because paper companies have incentives to replenish their forests, large demands for paper lead to large forests, while reduced demand for paper leads to fewer farmed forests. When foresting companies cut down trees, more are planted in their place. Most paper comes from pulp forests grown specifically for paper production. Many environmentalists point out, however, that farmed forests are inferior to virgin forests in several ways. Farmed forests are not able to fix the soil as quickly as virgin forests, causing widespread soil erosion and often requiring large amounts of fertilizer to maintain while containing little tree and wildlife biodiversity compared to virgin forests. Also, the new trees planted are not as big as the trees that were cut down, and the argument that there will be more trees is not compelling to forestry advocates when they are counting saplings. In particular, wood from tropical rainforests is rarely harvested for paper. Rainforest deforestation is mainly caused by population pressure demands for land. With many materials that can be recycled, such as fossil fuels and metals, there is only a finite amount of those resources, and people continue to use more of them all. Report asserts to reduce the current usage greatly and reuse them much more efficiently. For example, only 1% of rare earth metals are reused. Those materials cannot easily be recovered when a product that contains them is deposited in a landfill compared to if it was recycled. Possible income loss and social costs. In some prosperous and many less prosperous countries in the world, the traditional job of recycling is performed by the entrepreneurial poor such as the Karanguni, Zabaleen, the rag and bone man, waste picker, and junk man. With the creation of large recycling organizations that may be profitable either by law or economies of scale, the poor are more likely to be driven out of the recycling and the remanufacturing market. To compensate for this loss of income to the poor, a society may need to create additional forms of societal programs to help support the poor. Like the parable of the broken window, there is a net loss to the poor and possibly the whole of a society to make recycling artificially profitable through law. However, as seen in Brazil and Argentina, waste pickers informal recyclers are able to work alongside governments, in fully or semi-funded cooperatives, allowing informal recycling to be legitimized as a paying government job. Because the social support of a country is likely less than the loss of income to the poor doing recycling, there is a greater chance that the poor will come in conflict with the large recycling organizations. This means fewer people can decide if certain waste is more economically reusable in its current form rather than being reprocessed. Contrasted to the recycling poor, the efficiency of their recycling may actually be higher for some materials because individuals have greater control over what is considered a Euro waste. A Euro 1 labor-intensive underused waste is electronic and computer waste. Because this waste may still be functional and wanted mostly by the poor may sell or use it at a greater efficiency than large recyclers. Many recycling advocates believe that this laissez-faire individual-based recycling does not cover all of Societe Euro 1 registered trademark-S recycling needs. Thus, it does not negate the need for an organized recycling program. Local government often consider the activities of the recycling poor as contributing to poverty blight. Public participation in recycling programs. Between 1960 and 2000, the world production of plastic resins increased 25-fold, while recovery of the material remained below 5%. Many studies have addressed recycling behavior and strategies to encourage community involvement in recycling programs. It has been argued that recycling behavior is not natural because it requires a focus and appreciation for long-term planning, whereas humans have evolved to be sensitive to short-term survival goals. And that to overcome this innate predisposition, the best solution would be to use social pressure to compel participation in recycling programs. However, recent studies have concluded that social pressure is unviable in this context. One reason for this is that social pressure functions well in small group sizes of 50 to 150 individuals but not in communities numbering in the millions, as we see today. Another reason is that individual recycling does not take place in the public view. In a study done by social psychologist Sean Byrne, it was found that personal contact with individuals within a neighborhood is the most effective way to increase recycling within a community. In his study, he had 10 block leaders talk to their neighbors and persuade them to recycle. A comparison group was sent flyers promoting recycling. It was found that the neighbors that were personally contacted by their block leaders recycled much more than the group without personal contact. As a result of this study, Sean Byrne believes that personal contact within a small group of people is an important factor in encouraging recycling. Another study done by Stuart Oskamp examines the effect of neighbors and friends on recycling. It was found in his studies that people who had friends and neighbors that recycled were much more likely to also recycle than those who didn't. Euro 1 registered trademark T have friends and neighbors that recycled. Many schools have created recycling awareness clubs in order to give young students an insight on recycling. These schools believe that the clubs actually encourage students to not only recycle at school, but at home as well. Related journals. See also. References. Further reading, Ackerman, Frank. Why Do We Recycle? Markets, Values, and Public Policy. Island Press. ISBN 1-55963-504-5. ISBN 978-1-55963-504-2, Ayres, A.U. Industrial Metabolism, Theory and Policy, in, Allenby, B.R., and D.J. Richards, a unregistered trademark. The Greening of Industrial Ecosystems, a unregistered trademark. A unregistered trademark. National Academy Press, Washington, D.C., pages 23-37. Braunout, M., and W. McDonough. A unregistered trademark. Cradle to Cradle, Remaking the Way We Make Things. A unregistered trademark. A unregistered trademark. North Point Press, ISBN 0865475873. Huseman, Michael H., and Joyce A. Huseman. Techno-Physics, Why Technology Won. A unregistered trademark. T. Save Us or the Environment, a OE Challenge No. 3, Complete Recycling of Non-Renewable Materials and Wastes. A New Society Publishers, Gabriela Island, British Columbia, Canada, ISBN 0865717044, ppA 135. A 137. Porter, Richard C. The Economics of Waste. Resources for the Future. ISBN 1-891853-42-2, ISBN 978-1-891853-42-5, Tierney, John. Recycling is Garbage. The New York Times. External links, Recycling at DMOZ, study debunks myths around co-mingling. Recycling Waste World. May 10, 2010.